to neural elements of neural network and deep learning, part 4. I am Tiniam V. Ganesh. So let's get started. This fourth part also is based on the following two courses: Neural Networks and Deep Learning by Professor Andrew Ng at Coursera, Neural Networks and Machine Learning by Professor Jeffrey Ng at Coursera, and the two books, Neural Networks and Deep Learning by Michael Nielsen and Deep Learning book by Ian Goodfellow, Yoshua Bengio, Ron Cole, and other material from the internet. Now in part 3 I had shown you a simple three-layer neural network where we had the inputs x1, x2 and x3 and a bias term, and we have this is the input layer and we have an output layer and we have one hidden layer. These circles are activation units which could be any nonlinear functions, for example sigmoid, tanh, ReLU or leaky ReLU. If we have just one hidden layer, it's called a neural network. If we have more than one hidden layer, then it's called a deep learning network, and you could have as many activation units in each of your hidden layers. So this first one is a two-layer neural network where we have an input layer and we have inputs x1 and x2 plus a bias and an output layer. And here we have a three-layer neural network where we have an input layer, an output layer and a hidden layer in between. There is also a convention where the hidden layer is not counted. So this is taken to be a one-layer neural network, so just an output layer. And this second three-layer neural network which I had shown in part 3 is actually a two-layer neural network with just one hidden layer, one output layer. However, I'll be using the convention where I'll also be counting the input layer, so I'll consider this as a three-layer neural network. Now in both parts 2 and parts 3 we had seen how if we change the weights in any layer by an amount delta W, then the output also changes by a small amount delta output, and also this results in the corresponding change in the error or the loss. So if the loss was just loss before the change in the weight, then a change in by delta W in the weight would result in a change in delta loss. And the whole objective behind gradient descent, we do this in the forward propagation cycle, and each time, and we go through a backward propagation cycle. We do this to find the combination of weights which results in the lowest possible loss for all samples in the training data set. And this is done by this process known as gradient descent, where we start with some initial value of the weights Wi and Bi. We do one cycle of our propagation, that is we compute the linear activation, then we go through all the activation units, we compute the loss, and we know the cost is basically the average of the loss over all the training samples. So once we compute the total cost, we try to compute the gradient of the cost with respect to the weights and bias through a method of backward propagation. And once we compute how the cost varies with respect to the weights and the bias, then in each iteration we take the current weight and we subtract from the current weight how the cost varies with respect to the weights and bias, multiplied by a value alpha, and we get a new set of weights here. And with this new set of weights, after the first iteration, we do another cycle of forward propagation, we compute the cost, and then we do a cycle of backward propagation where we compute how the cost varies with respect to the weights and bias, and then apply gradient descent formula to get a new set of weights and bias. So we do this repeatedly till and our cost will continuously keep dropping as long as we have chosen the correct alpha. And then we finally stop when we have what we think is the lowest cost. At that point, we will have a set of weights for all the input and the hidden layers, and that set of weights is basically our neural network or a deep learning model, which will also apply to all data in the test set. So here again I'm just going through the three-layer neural network which we had seen in part 3. So you have two inputs x1, x2 and a bias, and the weights for the input x1 is W1 W11 superscript 1, W12 superscript 1, and W13 superscript 1. And similarly for x2, we have weights W21 superscript 1, W22 superscript 1, and W23 superscript 1, and then we have the bias. And so we compute the linear activation Z11 is equal to W11 superscript 1 x1 plus W21 superscript 1 x2 plus B1, and Z12 is W12 superscript 1 x1 plus W22 superscript 1 x2 plus B1, and Z13 is W13 superscript 1 into x1 plus W23 superscript 1 into x2 plus b1, and then we compute the activations on the other side, which could be any linear activation. In this case I've used the tan h, so a11 is tan h of z11, a12 is tan h of z12, and a13 is tan h of z13. Similarly on layer 2, we first compute the linear activation. Z21 is equal to w11 superscript 2 a11 plus w21 superscript 2 a12 plus w31 superscript 2 into A13 plus B2, and then we compute the activation in the last layer. Since we are going to use a biotic classification, we're going to take the sigmoid activation function and we're going to use sigmoid of Z21. Now again, if I rewrite this in matrix form, we have Z1 is a column vector, and we can rewrite as a matrix of the weights into the inputs plus the bias. So basically you can see this matrix multiplication. So basically this row into this column will essentially give you this row. Similarly, you take the second row and multiply by this column plus the bias will give the second row. So this is just the matrix form of this, and then we take the activation. Capital A1 is a column vector A11, A12, and A13, which is equal to tan h Z11, tan h Z12, and tan h Z13. Similarly, layer 2, the matrix form is capital Z2 is equal to the vector row vector W11 subscript 2, W21 subscript 2, W31 superscript 2 into matrix multiplication of Z11, Z12, and Z13 plus bias. So this will reduce to this particular equation, and lastly A2 is equal to sigmoid of Z21. So the forward propagation equations we can write as Z11 equal to capital W1 into X plus B1, where W1 is the weight matrix and X is our input vector, and assuming you have m samples, this will be a matrix of a vector of nx into m size, and A1 is equal to tan h of Z1, and Z2 is equal to W2 into A1 plus B2, and A2 is equal to sigmoid of Z2. And in the backward propagation, as I said, the whole goal of gradient descent and the need to do forward propagation, backward propagation is to determine how the loss or the cost varies with respect to the weights in the layers, in the output layer and the hidden layer. So we really need to find dou L by dou W2 and dou L by dou B2 and dou L by dou W1 and dou L by dou B1. These are the four key items we need to compute, which will allow us to perform gradient descent, and I get to the weights which will result in the lowest cost. So since you're using a sigmoid activation unit, the loss will be L of A2y is the log loss, is minus y log A2 minus 1 minus y log 1 minus A2, which I had shown in my part 2. And if I take the derivative of this loss, it will be dl by dA2 is y of minus y of A2 plus 1 minus y into divided by 1 minus A2. And dou L by dou Z2 is dou L by dou A2 into dou A2 by dou Z2. Dou L by dou A2 is this term here, which you have already seen, minus y divided by A2 plus 1 minus y divided by 1 minus A2. And the derivative of dou A2 by dou Z2 is basically the derivative of the sigmoid, which we have seen in my part 2 is A2 into 1 minus y2. And if I multiply these two and reduce it, I'll get A2 minus y. Now dou L by dou W2, dou L, how does it vary with respect to dou W2? Is dou L by dou A2 is by chain rule, dou L by dou A2 into dou A2 by dou Z2 into dou Z2 divided by dou W2. Now dou L by dou Z2, which is these two terms, is A2 minus y, which I put here, and dou Z2 by dou W2, dou Z2 by dou W2, if I take the derivative dou Z2 by dou W2, this term will become a constant, so I'll be left with I will take the derivative of this term, which will give me A1. So I will be dou Z2 by dou W2 is A1, and dou L by dou B2 is basically again with the chain rule dou L by dou A2 into dou A2 by dou Z2 into dou Z2 by dou B2. Now this term we have already seen is A2 minus Y, and dou Z2 by dou B2, if I take dou Z2 by dou B2, this term becomes the constant, becomes dou B2 by dou B2, which is 1. So this will be A2 minus Y, and dou L by dou Z1 is basically expanding the chain of dou L by dou A2 into dou A2 by dou Z2 by dou A1 into dou A1 by dou Z1. Now we have already seen that dou L by dou A2 to dou A2 by dou Z2 is A2 minus Y. We have seen this here. And dou Z2 by dou A1, dou Z2 by dou A1 is basically W2, which is here. And the last dou A1 by dou Z1, basically the derivative of this activation unit, which is the tan H. We have already seen in part 3 it is 1 minus A1 squared. So it is basically this set of equations. And lastly, dou L by dou W1 is dou L by dou A2 by dou Z2 by dou A1 by dou Z1 by dou W1. Basically, you just have to expand this into the chain rule from the back towards this point. And if you use this, will finally become A2 minus Y. It will be basically all you saw in the previous term. It will be A2 minus Y into W2 into 1 minus A1 square. It will be derivative of tan H into X, because dou Z1 by dou W1 is X. And lastly, we have dou L by dou B1, again using the same thing. Will be it will be the same as above, except that we'll dou Z1 by dou B1 will be 1, so you'll be left with A2 minus Y into W2 into 1 minus A1 square. So once we have these four values, dou L by dou W2, dou L by dou B2, dou L by dou W1 and dou L by dou B1, we can use these values for our gradient descent. So we go through the cycle and in the forward propagation, compute the loss. Then we go to the backward propagation and find how the cost varies with respect to the weights W1 and W2, and the cost was varies with respect to the bias B1 and B2. And then we take the current value of the weight and subtract from it this cost multiplied by alpha, which is the learning rate. And similarly, we take the current value of the bias and subtract from it how the cost varies with respect to the bias, and multiplied by a factor of alpha, which is the learning rate, and get the new weights and the new bias. So we do this repeatedly till we arrive at, and for each iteration we compute the new cost, and where the cost is basically the average of the loss over all the training examples. And we plot how the cost varies for each iteration. The cost varies with the number of iterations, and when we perform this gradient descent, the cost continues to keep dropping as long as you have chosen the correct value of alpha, and we can finally stop when we are satisfied that we reached a very good value of the cost. And then that set of weights which we have computed for all our layers will be our deep learning model, which you can use on a new test set. Now we saw a basic 3-layer neural network. Now let us look at a 4-layer neural network, and we would like to derive the equations for a L-layer multi-unit deep learning network. That is, regardless of the number of layers and regardless of the number of units in any layer, we would like to compute the generalized equation. Now let us assume that we have inputs x1 up to xi and a bias term, and then we have two hidden layers, so here and one output layer. So z1, so we have the equations if the same for this 4-layer neural network. Z1 is the linear sum of the inputs, so it's W1 A0 plus B1, where A0 stands for the inputs or the features. So Z1 is W1 A0 plus B1, and the activation in the first hidden layer is A1 is equal to G of Z1. Here G could be any activation unit. So since you want to derive the generalized form for L-layer neural network, we don't specify what our activation function is. It could be anything. So it could be a tan H or a ReLU or a leaky ReLU or a sigmoid. And then Z2 is equal to W2, the weight in this layer, multiplied by the input from the previous layer, which is the activation unit A1 plus B2, and A2 is again some activation function G of Z2, and then Z3 at the output layer is W3 into A2 plus B3, and since if we are going to be using we're going to be doing binary classification, we'll have A3 is equal to G of Z3, where G is the sigmoid activation function, or you could have any other activation function. Now, assuming for our simple case, we will assume that we are going to use a binary classification. So we know the log loss is L of A3 y is minus of y log A3 minus 1 minus y log of 1 minus A3. So if I take this, we have already seen dou L by dou Z3 is dou L by dou A3 into dou A3 by dou Z3. Dou L by dou A3 is the derivative of the log loss, which will be minus y divided by A3 plus 1 minus y divided by 1 minus A3. And dou A3 by dou Z3, if we had a sigmoid activation function, it will be A3 into 1 minus A3. And hence, if I take these two terms and multiply and reduce it, I'll get A3 minus y. Now the next dou L by dou A2 is dou L by dou Z3 into dou Z3 divided by dou A2. Now dou L by dou Z3 is A3 minus y, and dou Z3 by dou A2 is W3. Dou Z3 by dou A2, dou Z3 by dou A2, this term becomes constant. So dou Z3 by dou A2 is, dou Z3 by dou A2 is W3, because dou Z3 by dou A2 is W3. Similarly, dou L by dou Z2 is dou L by dou A2 into dou A2 by dou Z2. Now dou L by dou A2 is A3 minus y into W3. This is what we saw in the equation 1a. And dou A2 by dou Z2, that is, we have some activation function, we want to take the derivative of this activation function. Since you want to keep it in a generalized form, we take this derivative as g dash of Z2, where g is the activation function, its derivative we take it as g prime of Z2. Next, dou L by dou W2 is dou L by dou Z2 into dou Z2 by dou W2. So dou L by dou Z2, we already seen. Okay, dou L by dou W2 is dou L by dou Z2 or dou Z2 by dou W2, and dou L by dou Z2 we keep it as it is, and dou Z2 by dou W2. Dou Z2 by dou W2 is basically A1, so we write it as A1. And lastly, dou L by dou B2 is equal to dou L by dou Z2 into dou Z2 by dou B2, but since dou Z2 by dou B2 is equal to 1, we just leave it as dou L by dou Z2. Now let us take for this first layer, dou L by dou A1 is equal to dou L by dou Z2 into dou Z2 by dou A1. We leave this term as it is, and dou Z2 by dou A1 is W2. Now dou L by dou Z1 is dou L by dou A1 into dou A1 by dou Z1, and we write this as dou L by dou A1. Dou L by dou A1, we have seen it here as dou L by dou Z2 into W2. So this becomes dou L by dou A1 into W2 into, and we take the derivative of dou A1 by dou Z1, it becomes G prime of Z1, and dou L by dou W1 is dou L by dou Z1 into dou Z1 by dou W1, which will become this dou L by dou Z1 into A0, and dou L by dou B1 is dou L by dou Z1. So by just inspecting these equations, we can write where they all have a generalized form, where there is one, the number 1, I will take it as the layer L, dou L by dou L, AL is dou L by dou 1 plus 1, 2, so by dou Z L plus 1 into WL plus 1. Dou L by dou ZL is equal to dou L by dou AL, where for 1 I just replace L, and I will say it is into G prime of ZL. And lastly, dou L by dou WL is equal to dou L by dou ZL into A0, so L minus 1, and dou L by dou B1, dou L by dou BL is equal to dou L by dou ZL. So in the forward propagation cycle, we give the input features X or A0 into using the weights and the bias, we compute the activation, linear activation and the activation, and then we pass it to the second next layer with the weights W2 superscript 2 and bias superscript 2, and we get the activation out of the second layer, and so on. We go in the forward direction. In the backward direction, then we have the loss, and then we take the derivative of the loss with respect to the activation in the last layer, and then we compute from that how the loss varies with respect to the weights in the previous layer, and then we also compute how the loss varies with respect to the activation in this layer, and so on. We go in this forward and backward direction, and so at the output in the backward propagation is this dou L by dou W I and dou L by dou Bi in each of the layers, and once we have this, we can use it to in gradient descent to keep iterating and get the set of weights and bias which will give us the lowest cost. So these are the generalized form of the equations. ZL is equal to WL into AL minus 1 plus BL, which is the forward propagation linear activation, and then the activation in the Lth layer is some function G of ZL, where G could be any activation function, sigmoid or tanh or ReLU. And the backward propagation dou L by dou AL is dou L by dou ZL plus 1 into WL plus 1, and dou L by dou ZL, that is the activation in the Lth layer, is dou L by dou AL into G prime of ZL, but G is any activation function, tanh ReLU or leaky ReLU, and dou L by dou WL is dou L by dou ZL into AL minus 1, and dou L by dou BL is dou L by dou ZL. So once we have generalized forms, we can do this forward propagation, compute the cost, and then the backward propagation we can find how the cost varies with respect to the weights and the cost varies with respect to the bias, and with the weights we have in that iteration, we subtracted using the gradient multiplied by a small value alpha, and for the bias we subtract how the cost varies with respect to the bias and get the new bias, and then we get a new value of weight and the biases. Then we again do another cycle of forward propagation, compute the new cost, compute the new gradients, and then we keep repeating till we get a low cost. So and ideally what should happen is, for different values of alpha, if you keep plotting the cost versus the number of iterations, your cost should keep on dropping, and as you go. However, if you choose incorrect value of alpha, it could increase, so that is very important. So to test out my implementation of an L-layer deep learning network, to make it more interesting, I actually use the equation of a lemniscate of a Bernoulli, and it has this interesting shape of like this, where the yellow you could consider as 1 and all the black dots as 0, and I use my multi-layer multi-unit deep learning network to identify this fairly complex nonlinear boundary, and this is what I got for Python. This is the value in R, and this is how I got it in Octave. So Python, it may appear that it didn't do a very good job, Python and Octave, but the key point is we have a lot of parameters and knobs to tune in our new deep learning network, because we have different numbers of hidden layers, the number of units in each hidden layer, and the learning rate alpha, and the number of iterations. So by properly choosing these hyperparameters, we can get a very good performance of the deep learning network. I will be discussing how to tune these hyperparameters in a subsequent lecture, but for now these three examples show how you can use a multi-layer multi-unit deep learning network with using the generalized equations, which can be easily implemented using any of the languages like R, Python, or Octave. Thank you. So that ends part 4 of Elements of Neural Network and Deep Learning.